In this video, we're going over the concepts of chapter 2, which is titled Atoms and Radioactivity. We are going to look in this video into what is an atom and what is its components, what is atomic number and atomic mass, and how we can derive that information from the periodic table. And we're going to proceed to talk about isotopes. In section 2.1, we're going to look at atoms and their components. Let's first define what is an atom. An atom is a basic unit for a chemical element. So atoms is what elements are made out of. We can observe in the first image, I'm going to zoom in, that here we have lithium metal, which is an element. Specifically, lithium metal is element 3 in the periodic table. We can observe in that second image that lithium metal, which is what we observe with our eyes, is actually made of lithium atoms. And in this illustration, those lithium atoms are represented by those different white balls that we see there. Now, each atom has the following subatomic particles. We can see that atoms are composed of protons, neutrons, and electrons. And we can see in that third image that they are depicted in their location in an atom. In the nucleus of the atom, we are going to find specifically neutrons, which are illustrated by those white spheres that we can see there. And then we have protons. Now, outside of that nucleus, we're going to see electrons. In this table that we have on the slide, you can see that we can observe the name of the particle, the symbol that we utilize as an abbreviation, what is the charge for the subatomic particle, what is their mass given in units of AMU, in other words, atomic mass units. And lastly, we see their location in an atom. So as we go into the table, we can observe that specifically a proton, which lives in the nucleus of an atom, is symbolized by the letter P, or a P that has a superscript that has a plus sign. The charge of a proton is going to be +1, and the mass of a proton is 1.007 AMU. Neutrons, as you can see in the middle, which are also located in the nucleus, are symbolized by an N or an N to the 0. They have a charge of 0, so essentially they have no charge, and their mass is 1.008 AMU. So the mass of protons and neutrons is very similar. Lastly, we have electrons. And electrons are going to be symbolized by a letter E that has a negative sign as a superscript. Overall, they have a charge of -1. We can observe that they are outside of the nucleus. And lastly, we can observe that when we compare electrons to both protons and neutrons, they have a lower mass. Specifically, it is 0.00055 AMU. Now, all this information about subatomic particles that are part of an element has already been incorporated into the periodic table. And in section 2.2, we can observe how if we look at the information given in a box for the periodic table, we can derive what are the protons, what are the neutrons, and what are the electrons for any atom. As we can see in the example here for element 19, in other words, potassium, which has the symbol K, many periodic tables are going to have this information. Typically, you will see the symbol and the number that is above the symbol, that is known as the atomic number for an element. Now, if we take that information and we incorporate it into how does that lets us know about protons, neutrons, and electrons, understand that specifically the atomic number for an element equals the number of protons. So far in our discussions, we're just talking about ground state elements. And ground state elements are going to be elements that have not lost electrons and are not charged. So in this instance, the atomic number is also the number of electrons for an atom. Another piece of information that we have given in the periodic table is going to be atomic mass. In the atomic mass, specifically, in order for us to derive the subatomic particles, specifically the neutrons, needs to be rounded to a whole number. So once we take that atomic mass that we can see that is usually given below the chemical symbol for an element, we can rearrange the equation that you observe here and determine specifically that the number of neutrons is going to be specifically when you take the mass number, and remember that that needs to be rounded to a whole number, and you're going to subtract it from the atomic number. Let me just put a note that this needs to be rounded to a whole number before we decide to determine what are the number of neutrons for a particular element. As an example, in the following table, we are given some pieces of information, and then if we are given some pieces of information, as we can see in the table, which include the name of the element, the symbol of the element, atomic number, mass number, number of protons, neutrons, and electrons, we can actually derive what is the identity of particular elements. For the purpose of this video, I'm going to do specifically the second row. So if we look in the second row, it has been given to us the name of the element, and it's also been given to us the atomic number for the element. And from there, we need to make sure that we fill in element symbol, mass number, number of protons, neutrons, and electrons. Let's proceed. Since I know that I'm looking at the element chlorine, and its atomic number is 17, looking at the periodic table, I can observe that the symbol for this element is a capital C followed by a small case L. Next, since I know the atomic number, or that atomic number has been given to me, I can already determine what is the number of protons and what is the number of electrons. Remember that the atomic number for an element is going to equal the protons. Also, it will equal the number of electrons. Because so far, we're just talking about ground state elements. So the number of protons is going to be 17. The number of electrons is also going to be 17. Then I have the mass number. So that mass number is going to be where I take that atomic mass for the element and I round it to a whole number. So if my value is 35.45 and I round it to a whole number, then it becomes 35. But atomic mass is going to be the value that I see in the periodic table, 35.45, and it has a unit of AMU. In order to find the neutrons, remember that this is where I take my mass number minus atomic number. That's what's going to give me the neutrons for an atom. So when I take 35 minus 17, that means that for chlorine, I have 18 neutrons. Understand that for the neutrons, you cannot take the atomic mass with its decimal value because we don't have partial neutrons. We utilize a whole number. Then we proceed to look at isotopes and how does that look into atomic mass. So let's first define what it is an isotope. An isotope is going to be atoms of the same element that have different atomic mass. In other words, atomic number. So when it comes to this, understand that this is based on experimental data. In this table 4.7, which has been derived from a different textbook resource, it actually illustrates the isotopes, for example, for the element magnesium. So we can see here the different names of the isotope, which is isotope magnesium 24, magnesium 25, and magnesium 26. That value that we see next to the symbol for magnesium represents the mass number. When we look at the information given in the following table, we can observe that since we're talking about magnesium, every single one of these isotopes is going to have 12 protons and 12 electrons. Because remember that that information actually comes from the atomic number. And since we're talking about magnesium, they must have the same atomic number. Now, the difference between different isotopes of the same element is going to be specifically the number of neutrons. As we can see, magnesium 24 has 12 neutrons, magnesium 25 has 13 neutrons, and lastly, magnesium 26 has 14 neutrons. Having a different number of neutrons results in isotopes having a different mass number. And you can see in that second to last row where we see the differences in the mass number of those magnesium atoms. You may be wondering, why are isotopes important? Well, all of this is actually obtained from experimentation, because in the last row of this table, we can observe percent abundance. Understand that scientists have actually explored the presence of elements throughout the Earth crust and seen what is the chances that you're able to find an isotope for an element, and that's what is given by the percent abundance. So when we compare magnesium 24, 25, and 26, we can see that magnesium 24 has the highest percent abundance. What that means is that if there's a sample of Earth crust and you are able to study what type of magnesium isotope is found, then you will see that the most common one out of these three is going to be magnesium 24. Moreover, it is important to know that even though we're not going to explore in this class, the concept of isotopes is actually being utilized to calculate the atomic mass of an element. So when we look at the periodic table, these values that we see for that atomic mass or mass number for the elements, it is actually a weighted average of the mass of all the isotopes that exist for a particular element. Some elements have one isotope, some elements have 2, 4, even 6 isotopes. So understand that every element has its own number of isotopes, and that concept has been incorporated already into the periodic table. Lastly, when it comes to isotopic information, we actually have a notation that it is utilized in order to represent an isotope. And as you can see in this notation that is given on the right side of the slide, this is known as isotopic notation. In an isotopic notation, we can observe that first we're going to write the element symbol. Here you can see that that capital U is representing the element uranium. Then on the top left corner of my element, the mass number is incorporated. So for this atom of uranium, we can see that the mass number is 235. In the bottom left corner for the atoms or for the element's chemical symbol, we can see the atomic number. And we can see that for uranium, that is 92. So if we go back to the work that we did in the previous slide, and we want to write specifically the isotopic notation for this isotope of chlorine specifically, we could write it in the following manner. I'm going to write it on the side, even though I have space in the bottom. And the isotopic notation for this isotope of chlorine will be written as the following. We have the chemical symbol, Cl. In the top, I'm going to put the mass number. Remember that that is the atomic number rounded to a whole number. In the bottom, I'm going to put specifically the atomic number for my element, which is 17. So you can see that this is the isotopic notation for this isotope of chlorine.